There are rare moments in astronomy when a single photograph dose in T simply add to our knowledge, it detonates it. When it doesn't confirm what scientists expect, but instead reveals something so sharply contradictory that the entire field is forced to stop and rethink its assumptions. In late November 2025, under the unbelievably clear skies above Haleakalā, on the big island of Hawaii, such a moment arrived. And the shock wasn't delivered by some billion-dollar flagship telescope. Not by the James Webb Space Telescope, not by a NASA Deep Space Probe, but by a commercially available C-STAR S50 smart telescope, the kind of device any dedicated amateur can buy online. Yet the image captured that night has become the most geometrically revealing, scientifically unsettling, and conversation-shifting view of the interstellar object now designated 31 ATLAs. What that modest telescope recorded was something that should not exist. A perfectly thin, perfectly straight antitail, a line of material streaming toward the sun instead of away from it. And doing so with a knife-edge precision that comets simply do not produce. This antitail is no artifact, no camera malfunction, no processing trick. It persisted after multiple independent observers restacked the frames, recalculated point spread functions, removed noise patterns, and even verified the raw pixel channels. The structure is genuine. And if it is genuine, then it forces a profound revision in how comets shed material. How dust behaves when exposed to intense solar radiation, and what happens to small bodies that wander across star systems before falling into ours. Antitails themselves aren't new under the right geometry when Earth crosses a comet's orbital plane. The dust fan can appear like a line pointing sunward, but 3I-ATLAs completely violates the expected behavior. Natural antitails look wide, hazy, soft-edged, because comets emit a chaotic mix of particles, large grains, small grains, translucent ices, heavy rocks, unevenly shaped fragments, and debris. Seen edge-on, that dusty sheet appears like a broad, triangular smear. But the Haleakalā image didn't show a smear. It showed a needle, a razor, a thin, luminous filament, so narrow that it looks as though it has been drawn with a ruler across the cosmos. To produce such sharpness, the dust grains must be nearly identical in size, mass, and reflectivity, and must be released at nearly identical velocities. Nature almost never produces this kind of uniformity, and yet the tail is dazzlingly bright. Brightness suggests reflective icy particles, which are normally very lightweight and easily pushed outward by sunlight. But a tail this straight should require heavy dust, not light dust. Metal-rich grains, rocky fragments, dense exoplanetary core shards, materials that are normally much darker. And yet 3I-ATLAS's antitail is both brilliant and rigidly collimated. In other words, highly reflective yet apparently massive. This is the contradiction that has ignited the scientific debate. If the dust is bright, it shouldn't hold its shape. If it is heavy, it shouldn't shine like this. The object seems to be doing both simultaneously, and that duality challenges our understanding of cometary physics. Some researchers argue the explanation may lie in the object's origin. Maybe 3I Atlas isn't a typical icy visitor like Borisov. Perhaps it's a fragment from the metallic core of a planet shattered in a distant star system. A chunk of differentiated geology, shedding uniform grains as its outer layer sublimates. Others propose a monolithic nucleus, rotating so steadily and symmetrically that it releases dust like a finely tuned cosmic machine. And then there are the more controversial possibilities, ideas that hesitate on the edge of mainstream science. A few theorists, including some from Avi Loeb's research community, point out that uniformity on this scale is extremely difficult to achieve through natural means. Uniform particles, uniform motion, uniform alignment. They are not proposing aliens. They are proposing that the current physical models may not fully apply to this object, that the source of the tail, its acceleration, and its stability may involve physics we haven't yet accounted for. The Haleakalā image refuses to collapse neatly into established categories. What has intensified the mystery even more is the object's behavior beyond the tail. 31ATLAs appears unusually stable. Its rotation does not show the rapid brightness flicker expected from an irregularly shaped comet. Its inner coma looks structured, not chaotic. Its non-gravitational acceleration has no corresponding visible jet. Night after night, amateur and professional astronomers watch it, expecting turbulence, expecting the antitail to distort or expand. Instead, it remains astonishingly consistent. This stability contradicts the typical behavior of small interstellar visitors, which often tumble unpredictably after eons of wandering through interstellar space. Comets are supposed to be messy, inconsistent, volatile. Yet 3I Atlas behaves as though it possesses an underlying order, whether mechanical, magnetic, or geological. And what makes the whole situation even more remarkable is the role of amateurs in this discovery. The clarity of the Haleakalā skies, the rapid-fire exposures of the S50, and the new generation of AI-powered deconvolution tools allowed a backyard astronomer to produce a dataset so crisp that NASA and ESA have begun using it as a reference baseline. The image is now helping coordinate telescope time around the globe as the object races toward perihelion on December 19, 2025, as solar radiation increases in the coming days. Scientists are watching with extraordinary urgency to see what happens next. The antitail is merely a geometric projection. It will widen and fade as Earth shifts out of the orbital plane. But if it remains narrow, if it stays aligned even when the geometry changes, then our current explanations cannot survive. That scenario would imply internal mechanisms, magnetic confinement, or some form of dust regulation we do not yet understand. Perihelion is approaching fast, and with it the moment of truth for every competing model. The strange case of 3I Atlas has revealed something much larger than a single mystery. It has exposed how fragile our assumptions can be when confronted by data that refuses to behave. For decades, astronomy has been guided by predictable patterns. Comets behave like comets. Asteroids behave like asteroids, and interstellar visitors fit comfortably into one of those two categories. But this new object unsettles that simplicity. As 3I Atlas hurtles closer to the Sun, its behavior threatens to rewrite the manual on how dust survives long journeys through the void, how fragments evolve when torn from their parent systems, and what unknown processes might sculpt them across millions of years in deep space. Its antitail is not just visually striking. It is scientifically provocative. The structure is so disciplined, so controlled, that it challenges the expectation of cosmic randomness. Nature does create order, but seldom with this level of precision across so many variables simultaneously: brightness, mass, velocity, alignment, symmetry. The heart of the scientific tension lies not in the photograph itself, but in what happens around it. Some teams say the simple explanation is best, that we are observing a highly uniform sheet of heavy grains released by a rotating metallic nucleus. These researchers argue that interstellar objects may naturally be more varied than we assumed, and that 3I Atlas may simply fall at the extreme end of that natural spectrum. But the opposing camp insists that the data cannot be force-fit into comfortable assumptions. They highlight that the object has demonstrated non-gravitational acceleration without visible jets, reminiscent of the unexplained forces acting on wobble. They point out that the tail's tight collimation has lasted longer than projection-based antitails typically do. They emphasize that the object's S-brightness does not match the density required to maintain such structural rigidity. This group is not promoting extraordinary explanations. They are simply refusing to accept insufficient ones. Science does not grow by ignoring mismatches, it grows by chasing them. As the calendar moves toward December 19th, the stakes rise. Perihelion is more than a date, it is a stress test. Solar heat will increase dramatically. Volatile materials will erupt. Dust production will spike. The antitail is a fragile, geometry-dependent coincidence. It will collapse under these conditions. But if it holds its razor-thin line, if it stays coherent while the object experiences its most intense heating, then the scientific landscape changes. The explanation will no longer be a matter of geometry. It will require new physics or new geological origins. It will demand that we rethink what interstellar fragments can be made of, how they maintain structural order, how dust can behave like a controlled stream instead of a chaotic plume. This is the most captivating part of the unfolding drama. We are watching the universe challenge us in real time. A citizen astronomer with a small telescope has set off a global scientific investigation. Observatories across multiple continents are preparing spectroscopic scans. Space agencies are updating their models. Everyone is waiting to see whether nature will offer clarity or deepen the confusion. And in this moment, 3.1 ATL forces us to confront a truth that astronomy occasionally forgets. The universe does not organize itself according to our expectations. It does not rewrite its behavior to match our textbooks. It is under no obligation to be simple, convenient, or familiar. The antitail of 3i ATLAs is more than a structure. It is a symbol of scientific humility, a reminder that discovery does not always arrive through billion-dollar instruments. Sometimes it enters our world through a backyard telescope, carried across the stars by an object older than Earth itself. And whatever explanation emerges in the coming weeks, natural or extraordinariate, will reshape our understanding of interstellar debris, long-distance geological survival, dust dynamics, and perhaps even cosmic engineering. We are witnessing an event that astronomers will reference for decades, the moment an interstellar traveler revealed that our models, our expectations, and our confidence still have room to grow. The universe is speaking through a thin line of dust, and it is telling us that its secrets are far from exhausted.